Good evening. I'm honored to present to you our research on a novel semi-independent approach for steady-state visual evoked potential-based brain-computer interface systems for amyotrophic lateral sclerosis. I'm Nuttika Yongsanguanchai, one of the group members, and the other group members' names are listed on the slide. Background information. ALS is a rare neurodegenerative disease impacting motor neurons. It affects a diverse range with 1.75 to 3 cases per 100,000 people annually. ALS unfolds in 5 stages, starting with mild symptoms like speech issues and muscle weakness and progressing to severe paralysis, often requiring tracheostomy and ventilation. Communication becomes a significant challenge in the advanced stages. Currently, wheelchairs are equipped with EOG and eye trackers. However, the accuracy is low and it lacks a strong control system. Therefore, BCI is a better alternative. Problem statement. For BCI, in terms of accuracy, the user-dependent methods has a higher accuracy but requires significant training. On the other hand, user-independent methods has a lower accuracy but requires less training. Secondly, extensive training is required. Thirdly, there's a limited information transfer rate. Patients can sometimes experience visual fatigue, and there's also risk in surgical procedures for invasive BCI. Similarly to BCI, the invasive form of NIV can cause discomfort and health risks for the patient. The operation often requires a caretaker, which can also be a challenge.
From the challenges outlined in our problem statement, we are excited to unveil a groundbreaking solution that aims to empower ALS patients through advanced technology. So we are introducing the semi-independent training SSVEP-based BCI communicator and ventilation control. To achieve optimal brain signal translation accuracy, we have implemented a semi-independent training approach combining user-independent and user-dependent training methods using convolutional neural networks. This is not only balances system accuracy, but also minimizing cognitive effort on the patient part. The graphical user interface, or GUI, of our model consists of 3 main elements as shown in this presentation. The first one is a messaging system using 3-stage SSVEP web spellers for effective communication. And the next one is a ventilator control for making adjustment. And lastly, a smart home control, allowing users to handle electronic devices in the home. Our model utilizes the 3-stage SSVEP web speller, which have high accuracy and high information transfer rates. This type of SSVEP spellers offer increased stability, reducing the burden of encoding multiple frequencies and simplifying the system. To combat mental and visual fatigue, we have incorporated a limitation period feature, preventing overexertion and ensuring a manageable user experience for individuals with ALS. Moreover, we have adopted an innovative paradigm of oscillating expansion contraction concentric rings, proven to have the highest anti-fatigue property. Additionally, the use of white color cues in a specific frequency range on a black background ensures minimal visual strain and fatigue. Our system prioritizes user comfort and control. Users can customize display settings such as brightness, intensity, background color, or font sizes. Ventilation control is a critical component of our solution. ALS patients can manually and automatically adjust ventilation settings, ensuring optimal breathing parameters. The system also includes an abnormal breathing detection and adjustment features, providing real-time monitoring for safety and comfort. Now, let's take a closer look to our flowchart summarizing overall of the methodology, expertly presented by Nathakorn.
Okay, after part of functionality of our proposed solution, let's begin to the methodology. So we will begin with the user, aka the patient. So patient provides data, and this data divided in 42 parts, which is 4 BCI parts and also the NIV part. So for BCI parts, SCARP AG signal will go through people searching, SSVEP's detection, classification, and the last one, translation, to make a command to controller so the user can select the text they want to communicate. And for the second part, NIV, the respiratory signal and data will go through the same process as BCI, and this will send the command to the controller so the user can adjust the variables of the breathing or the respiration to make their breathing more normal or in the normal, and they can call as their assistants.
For benefits and impact of the solution, improve communication and ventilation, real-time neuro-driven communication, user-friendly graphic user interface, minimize cognitive effort, and holistic support. Lastly, for conclusion and future project, in BCI part, it can be done by adding non-effective and compatible triggering methods, improving the word prediction, and researching for more feature extraction techniques that can maintain important feature better. Try applying task-related component analysis method to SSVEP classification. For NIV part, try applying R model apart from 3D CNN convolutional LS3M model. Develop a system for remote monitoring, allowing healthcare providers to adjust settings and monitor patients. Implement smart ventilation algorithms within the NLV component to dynamically adapt to the patient respiratory needs.